This lesson is about rational functions. A rational function is a function of the form f of x equals p of x over q of x, where the function p of x and the function q of x are both polynomial functions. Our ultimate goal here is to learn how to analyze rational functions and produce graphs of them. They share many of the same properties of polynomial functions, but can be trickier because there are places where rational functions are undefined and often behave differently as they approach positive and negative infinity. So let's look at some properties of rational functions that we'll need to learn to analyze. First is the location of zeros, the same thing as an x-intercept, the location of y-intercept, the locations of vertical asymptotes or holes, and we'll discuss what asymptotes are when we get to that point, the locations of horizontal asymptotes or oblique asymptotes, and finally, possibly using sign charts if necessary. Let's start with the location of zeros. So, a reduced rational function f of x equals p of x over q of x has x-intercepts when the solutions to p of x equals 0 are real numbers. So as an example, let's find out where does f of x equals x squared minus 5x plus 6 divided by the quantity x minus 4 have x-intercepts. Well, the basic idea is to always just set the numerator equal to 0 and solve. Okay, the numerator is the top part of your fraction, the denominator is the bottom part. So my numerator is x squared minus 5x plus 6. Now I'm just going to set that equal to 0 and solve. So I need to factor because it's a square. 6, we could factor into 3 and 2. And if those are both negative, then they would multiply to a positive 6 and add to a negative 5, so that's good. That means x equals 3 and x equal 2 are the locations of the x-intercepts. But one thing you want to be careful of when you provide your final solution, oftentimes the answer here needs to be written as a coordinate pair. And that is because the x-intercept is a location on the xy plane. So you need both the x and y values to locate those. So generally, the final answer for x-intercepts would look like 3, 0, and 2, 0, for instance, in this case. So I've expressed it as a point. Then there's 2 points where we have x-intercepts. And one thing I want to mention is normally when we're coming up with x-intercepts, we take a function and set it equal to 0 and solve. And the reason we're not doing that here is because, let's say hypothetically, I took my function x squared minus 5x plus 6 divided by x minus 4, and I set that equal to 0 and started to solve this. Well, my first step here would be to multiply both sides through by x minus 4, because I'm trying to get that factor out of the denominator, and that's really the only way of achieving that. So when I multiply x minus 4 times the left-hand side of this equation, the x minus 4 in the denominator gets canceled, and I'm just left with x squared minus 5x plus 6. And then when I multiply 0 times anything, 0 times x minus 4 cancels away, and it's still just 0. So effectively, It's just the numerator that makes a difference when it comes to identifying the location of x-intercepts. So that's nice. One thing that will be helpful, when you have a rational function, so if I have f of x equals x squared minus 5x plus 6 over x minus 4, before you go through and do analysis with this with any of these problems, it's generally going to be helpful, to not only have this in what's called expanded form, but to also have it in factored form. So if I just factor, before beginning the problem, if I just factor the numerator and denominator, these are probably steps that I'm going to have to do later on anyway. So it's generally helpful to just go ahead and do it from the start. And then identifying the x-intercepts from the factored form is just a matter of, looking at the x minus 2 and knowing that the value x equals 2 would be where the function would be 0, and so forth. So having it in both expanded form and in factored form is going to be helpful. Next up, let's take a look at the location of y-intercepts. A y-intercept occurs when x is equal to 0. So we want to find the y-intercept of the function f of x equals x squared minus 5x plus 6 over x minus 4. So if I want to determine where the location of where x is equal to 0, then I'm just going to calculate, I meant to do it in blue here, sorry. I'm going to calculate f of 0. So it's going to be 0 squared minus 5 times 0 plus 6 all over 0 minus 4. What happens is anything that had an x in it originally in expanded form becomes 0. And you only are left with, in this case, 6 over negative 4, which is negative 3 halves. And so essentially, the y-intercept occurs at the ratio of your constants. So this is the ratio of the constants, but it needs to be in expanded form in order to identify that. And then similarly to the x-intercept, the y-intercept is expressed as a point as well. So the coordinate pair here would be 0 for the x, because we're looking at where x is equal to 0, and negative 3 halves for the y. Vertical asymptotes. A reduced rational function f of x equals p of x over q of x has vertical asymptotes when the function is undefined. One thing I want to point out, I'll go ahead and point out now, when we saw the slide for the x-intercepts, the definition there also said that the f of x had to be a reduced rational function. So I'll discuss what it means to be a reduced rational function in a little while when we see what happens when it's not reduced. And you just kind of understand right now that there's no factors in the numerator and the denominator that are the same. And I'll explain it in more detail as we get along further in the video. So locating undefined points, you're basically looking to where the denominator is 0. So essentially, you can find vertical asymptotes by finding the solutions to q of x equals 0. So you're just taking the denominator and setting it equal to 0 this time. So x-intercepts, you set the numerator to 0. Vertical asymptotes, you set the denominator to 0. Vertical asymptotes, these are represented graphically by vertical dashed lines. A graph can never cross a vertical asymptote. It's a point where the function is completely undefined. So it'll always approach the asymptote, and it'll approach the graph going either to positive infinity or negative infinity, but it will never cross that asymptote. So let's look at an example. Let's locate the vertical asymptotes of this function right here. So f of x equals 2x squared minus x minus 3 over x squared plus 2x minus 8. So the location of vertical asymptotes is always where the denominator is 0. So I'm going to take my denominator, set that equal to 0, and solve. In this case, I'll need to do some factoring. So x and x multiply together to give me x squared. I think 4 and 2 should work for 8. I need one of these to be positive and one to be negative. So positive 4 and negative 2. That way they're going to multiply to negative 8, but then add to positive 2. So the locations of vertical asymptotes here, x equals negative 4 and x equals 2. And you don't need to change these into coordinate pairs because a vertical asymptote is a vertical line. And if you'll recall from earlier algebra, the equation of a vertical line is of the form x equals some number. So these are equations of vertical lines. So this is perfect. Similarly, as I mentioned before, this is another time where if you had started off the problem expressing the rational function both in expanded form as it is originally here in this case, and also in factored form, if it was in factored form, it would be very easy to see the location of the vertical asymptotes. So taking some time to change it into having it into both forms can really make your job easier as you're doing analysis here. Next up, we're going to talk about holes in the graph. If a rational function of the form f of x equals p of x over q of x is reducible, okay, so now we're talking about this reducible rational function, meaning that p of x and q of x have a common factor that can be canceled out, then this is the location of a hole in the graph, which is indicated with an open circle. Let's follow through with an example like this. F of x equals x squared minus 9 over x plus 3. Now, one thing I want to do is I want to come up with the graph of this on your calculator and see what that graph looks like to begin with. So let's start there. So here's the calculator, and what I want to graph here is the equation x squared minus 9 divided by the quantity x plus 3. Now, in class, I often ask students from the beginning, what do you think this graph will look like? Many students have answers like, well, maybe some sort of parabola because they see the squared term in there. And different kind of answers this way, where some from the last slide may be thinking, well, there should be an asymptote in here at negative 3. And these are great intuitive guesses. But then most students are actually very surprised to find out that the graph shows up as a line. They're very surprised to discover that. Why is this just a line? I mean, we know that a line, the equation of a line has to always look like y equals mx plus b. Well, my f of x here doesn't look anything like y equals mx plus b. But we could do a little bit of algebra with this. So let's do a little bit of algebra and see what we can determine from this. Okay, so if I express this in factored form, well, the numerator factors because it's the difference of squares into x plus 3, x minus 3. Now, there's a shared factor in the numerator and the denominator of x plus 3. We're free to cancel that out, but there's one other thing that we have to be careful of, and I want to explain that to you right now. The thing we have to be careful of is one of the strongest statements in mathematics is the statement of equality. Because when you're saying that two functions are equal, you're saying that they agree for every single value on a scale that is spanning from negative infinity to positive infinity, and every number in between. That's an extremely powerful statement. And equality fails if you can find just one single point where two things disagree. So for instance, my original function here, if I put x equals negative 3 in, that is undefined. It doesn't have any number because you get division by 0. But if I put negative 3 in down here, negative 3 minus 3 is negative 6. So they don't agree at that one particular point. They will agree at every other point, but at that one particular point, they don't. So in order for me to be able to say that f of x is equal to x minus 3, I have to be very careful, and I have to also say where x does not equal negative 3. Because that basically says for every other value of x, they agree. But at negative 3, they don't agree. Now, the function y equals x minus 3, that is, the form of a linear function. And if we graph that, so let me come over here on a graph, then here's what that will look like. So x minus 3, so y-intercept of negative 3, the slope is positive 1, so I'll just plug in a few points here. Hopefully I'm hitting those scale values right. And go in the other direction. The only time where something different happens is where x is equal to negative 3. So at this particular value here. So when x is negative 3, my function is supposed to be at negative 6, but it's undefined. So to make that undefined, I'm going to put a hole in that graph. Every other point here is on my line. It's just that one particular point where things disagree. So I have a hole in the graph. So this will happen anytime you have a shared factor in the numerator and denominator that will cancel out. And you'll end up with a hole in the graph. Now, let's go back to the calculator screen because there's something I want you to understand about the functionality of the calculator. On screen, where x is negative 3, oops, that's right here, the negative 6, there's no hole in the graph there. The calculator does not indicate a hole. It is there, it exists in the function. It's just the calculator does not indicate that there's one there. And most calculators will not indicate it. Some of the newer versions of the calculators do, but most do not. Here's why. So the calculator, when it draws a graph, all it knows how to do is to calculate a y value based off of a given x value for any inputted function and plot those points and then draw a line between 2 points. So let me show you what I mean. So when the calculator is doing its drawing, it comes along and when it's at, see, that's 3, 4, 5, so like -7. It calculates the height of the point and it finds a value there. Then it goes on to -6. Actually, the space in between the points is much closer than just unit by unit, but just hypothetically. All right, so then it finds that next point, and then it draws a line between them. Then it goes on to the next value, calculates where the y value should be, draws a line, goes to the next one, calculates a y value, draws in between. Then it gets to x equals -3, and it discovers, oh, it's undefined. So initially it doesn't draw anything. All right, then it goes to -2, and it draws a point. Then it connects that from the previous answer. So it essentially just skips over the whole by doing this process. So you need to be very careful a lot of times when you're working with rational functions to not rely so much on the graph that's provided to you in the calculator, because there's going to be differences that it's not necessarily showing you. And holes is one of those where it doesn't do a very good job of representing. All right, next up we will discuss horizontal asymptotes. Now, a horizontal asymptote represents the value that a function approaches as x approaches positive or negative infinity. To determine if a rational function has a horizontal asymptote, what we're going to do is compare the degree of the numerator to the degree of the denominator. And one thing that's kind of unfortunate is that there's some differences between horizontal asymptotes and vertical asymptotes. So vertical asymptotes tell you where the function is completely undefined, and you can't cross a vertical asymptote. And you can have any number of vertical asymptotes. When it comes to horizontal asymptotes, the maximum for any function that you could possibly have is 2. So it's just the value that x goes to as your function, the value that your function goes to as x goes to positive or negative infinity, which could only be one of 2 numbers. With rational functions, it's only ever going to be 1. And horizontal asymptotes, you can cross any number of times. There's examples of functions that cross your horizontal asymptote an infinite number of times. It's just as you get further and further toward infinity, your graph is approaching that asymptote. Now, to determine the location of horizontal asymptotes for rational function, you need to remember these rules here. So first, if the degrees are bottom heavy, you're going to have a horizontal asymptote at y equals 0. So if the degrees are bottom heavy, what that means is that the degree in the denominator is larger than the degree of the numerator. Next, if the degrees are equal, there's going to be a horizontal asymptote at the ratio of leading term coefficients. Next, if the degrees are top heavy, so there is a higher degree in the numerator than the denominator, then there's no horizontal asymptote. However, if they just happen to be top heavy by 1, you have what's called an oblique asymptote. So let's look at these, some examples, and see how these rules apply. They're actually very straightforward. So if I have f of x equals x squared plus 3x minus 5 over 2x squared minus 1, then the degree of the numerator is 2 because the highest exponent is 2. The degree of the denominator is also 2. So the degrees are equal. And when the degrees are equal, you take the ratio of leading term coefficients. And remember, from polynomials, the leading term coefficient is the multiplier that's on the term that has the highest exponent. So in this case, I have a horizontal asymptote at 1/2 because the coefficient on my x squared term in the numerator is understood to be 1. The coefficient on my leading term in the denominator is 2. So 1 divided by 2, I'm making a ratio or a fraction of those. So there's my horizontal asymptote. Next up, in this equation, the degree of the numerator is 1. The degree of the denominator is 2. So the highest exponent in the numerator is just 1, so x to the first power, that is. And in the denominator, it's 2. So this is bottom heavy. And when that occurs, if you look back up at your rules here, there's a horizontal asymptote at y equals 0. So this rational function has a horizontal asymptote at y equals 0. Next example, in this rational, the degree of the numerator is 3, and the degree of the denominator is 2. So now we have a fraction that is top-heavy in terms of degree. When it's top-heavy in terms of degree, that means there's no horizontal asymptote, but because this one just happens to be top-heavy by 1, there is an oblique asymptote. Now, when it comes to locating oblique asymptotes, what you have to do is, well, in this case, you would have to use polynomial division. In general, the examples that you'll be given in this class, you're going to be able to use synthetic division. And you're going to use synthetic division in order to express the rational in such a way that you end up with a linear equation plus some remainder, and that linear equation is what your oblique asymptote is. I'll show you an example of that in just a little bit here. All right, so oblique asymptotes. If the degree of a rational function is top-heavy by 1, then the rational function has what's called an oblique asymptote, which is a line equation of the form y equals mx plus b that directs how the function approaches infinity. This is found using polynomial or synthetic division, but as I just mentioned in this class, your examples will all be ones you can do synthetic division on because that's a little bit easier. Or maybe I should say a little bit faster because these take enough time already. So let's locate the oblique asymptote in this function. Well, I need to use synthetic division. So remember, in synthetic division, the polynomial in the denominator, you take the opposite of that constant value, kind of set it aside. Then the polynomial in the numerator, you take its coefficients and express them, along this way. And then I always kind of set these apart as I get my answers. You bring the 1 straight down, multiply that 1 by the 3, place that number here. Add the -2 and the 3 together, which gives you 1. Then 3 times 1 is 3, and then we get an 8 here. So basically what this means is this rational can be expressed as x plus 1 plus 8 over that original denominator. And if you'll notice, the x plus 1, this is a linear equation. And that's what we're looking for. We're looking for that linear equation right there, because that is the equation of our oblique asymptote. So in this case, the oblique asymptote is going to look like y equals x plus 1. Then when we go to graph it, since it's an asymptote, we just graph it as a dashed line, but following the equation y equals x plus 1. We'll do an example with an oblique asymptote, and that'll make more sense. Lastly, another thing that can be helpful if you're just not sure where things are supposed to go on your graph is a sign chart. And it can be used to determine where a function is positive or negative, and it can be helpful in graphing. It's not necessary to do. Generally, you can derive all the information off of a sign chart from other means, but it is a very easy way of coming up with what you're generally looking for. So what you do is put all of your x-intercepts and vertical asymptotes on a number line and use values between these numbers to test where the function is positive or negative. What happens is the only way that a graph can go from positive to negative is either passing through the x-axis, which is where you're going to have x-intercepts, or by having a discontinuity. And a location of a discontinuity is certainly a vertical asymptote, or actually a hole also. Let me go ahead and do that. So, and holes. It's not as common to change from positive to negative at a hole, but it is, I guess it is possible. So let's create a sign chart for this function right here. And I'm going ahead and writing it in factored form so that we don't have to go through the steps of factoring first. All right, so it's a number line. And I'm going to put the location of vertical asymptotes and x-intercepts on this line. So at -3, I have a vertical asymptote because, from the factor x plus 3 in the denominator. Then at -1, I have an x-intercept. And at +2, I have another x-intercept. So the graph can only change from positive to negative at any of these points. So I know that in between those points, the graph is either entirely positive or entirely negative. So the idea is to just pick one value in each of those intervals to test and see if the graph is actually positive or negative there. So for instance, in the first interval, let's say I choose -4. And I use that as a test value. Well, let's see what happens. So if I put -4 into my function, -4 plus 1 would be -3. -4 minus 2 would be -6. -4 plus 3 would be -1. So this would be 18 over -1, or -18. And so I get a negative number, which it doesn't really matter exactly what the number is. It just matters that it's negative. So what I've discovered is everything on that interval is going to be negative. Okay, let's move to the next interval. So x equals -2. So f of -2, -2 plus 1 would be -1. -2 minus 2 is -4. -2 plus 3 is 1, so this is going to be +4. So again, it doesn't really matter that it's +4, it just matters that it's positive. And go on to the next one. So x equals 0. So f of 0, so 0 plus 1 is 1, minus 2, 3, so it's -2/3. Just matters that it's negative. And lastly, if I do, say, 3, if I plug 3 into my function, 3 plus 1 is 4, 3 minus 2 is 1, 3 plus 3 is 6. The result is positive. So now I know that everything in that interval is going to be positive. And let me just show you on the calculator, what this graph looks like, and you can kind of see how the positive and negative things happen. So I guess I need to erase this stuff here. All right, now go to my y equals, and in the numerator I have the factors x plus 1 and x minus 2. Then, divided by, in the denominator I have x plus 3. Now a graph. Okay, so we can kind of see what's happening, although it looks like I might need to zoom out a bit. So let me change my Windows settings to maybe like -20 to +20. Oops. On my Y. Maybe I can see a bit better. Okay. All right, so the points that were of interest that I put on my sign chart. -3, which is right there. -1, which is right there. +2, which is right there. So if you'll notice, in terms of the graph being positive or negative, which is above the x-axis or below the x-axis, from the interval from -infinity up to -3, this part right here, well, just there we go. That is entirely below the x-axis. So if you'll notice, I have found that on that interval my function is entirely negative. So that is what I'm seeing. That is consistent there. And then between -3 and -1, this portion of the graph is entirely above the x-axis, so it's entirely positive, which is what I saw. And I'd probably have to zoom in, but you can kind of see this little portion's below the x-axis. And then from 2 on, it is entirely positive. So the only way a continuous graph can cross the x-axis, so the only way that a continuous graph can get from positive to negative is going through the x-axis. But if you have a point of discontinuity, like where an asymptote occurs, that is also a place where you could change from positive to negative. So that's why it's only necessary to put those points on the graph. One other thing I want to mention here, if you'll notice, the graph looks like it contains a vertical asymptote, and it sort of does, but it sort of doesn't as well. Here's what's happening. So remember how I told you the graph is drawn by calculating where a point happens and then playing connect the dots. So it's basically getting a point down here, and then you get to the asymptote, and it is undefined, so it skips that point. And then it has the next point way up here. Well, then it plays connect the dots. So then it just connects these 2 points here. That's where that, what looks like an asymptote, that's where it's coming from. More evidence that the calculator is not entirely to be trusted in this, these examples. Okay, let's move on to the next slide here. Okay, so in the next few slides I have some functions, some rational functions that I want us to graph. So our very first one here is f of x equals x minus 2 over x squared minus x minus 6. Now, as I mentioned, you're going to want to express this in both expanded form and factored form. So I'm going to go ahead and start right now factoring this thing. So 3 and 2 should work. because they would multiply to -6 as long as I have a -3 and a +2. And then that way they'll also add up to -1. Okay, so the things that I need to come up with: x-intercepts, y-intercepts, horizontal asymptotes, and vertical asymptotes. Now, we went through a lot of slides as to how to come up with each of these, and it probably seems like at this point this is going to be an overwhelmingly long process. I promise you it will not. For instance, x-intercepts, they occur where the numerator is 0. In this case, that would be at +2, but express it as a coordinate pair. So I have an x-intercept at 2, 0. The y-intercept is going to be the ratio of the constants. My constants are -2 and -6. So that's going to be 1/3, but make sure you express it as a point. Horizontal asymptotes, here my rational is bottom heavy. If you go back through your notes, you'll note that if the graph is bottom heavy, it has a horizontal asymptote at y = 0. If it has a horizontal asymptote, it does not have an oblique asymptote. That's no longer even an issue at all anymore. Vertical asymptotes occur where you have zeros of the denominator, which in this case are x equals +3, x equals -2. That really wasn't all that much work. Once you understand the concepts, applying them really isn't much work here. So let's put some things on the graph here. So the x-intercept is at 2, 0. That's there. Y-intercept at 0, 1/3. So about right there. Horizontal asymptote at y = 0. So I'm going to put a dashed line here at 0. Vertical asymptotes at +3 and also at -2. Okay. Now, the only other thing that might be useful is a sign chart, but that it's not always the case. I think in this case it would be helpful, and let me explain why here. So in this first interval, the graph has to either be the first interval is from -∞ up to -3. The graph will have to be either entirely positive or entirely negative. I know that for a couple of reasons. One, there are no x-intercepts in that interval. There's no way I could change from positive to negative. And the asymptotes guide the direction of your graph. So either on this interval, my graph looks like this, or my graph looks like this. The asymptotes bend your graph toward them. Okay? That's the only two options there. But without a sign chart, I can't really rule out either one at this point. So I'll do a sign chart. So on that interval, so up to -3, that was a vertical asymptote. And then I had +2 is an x-intercept. And you don't need to label these, I just do it out of habit. And +3 is another vertical asymptote. Okay, so say at -4. Let's see what's happening with my function. So it would be -4 minus 2, which would be -6, which is really only important that it's negative. Okay? In the denominator, it would be -7 times -4 plus 2 would be negative. So a negative times negative in the denominator would be positive, and in the numerator, it would be negative still. So this is a negative divided by positive. The result is going to be negative. And if you're unsure, just playing with only the signs, what I'm doing there, just use the numbers. If you use the numbers, you'll come up with an actual number of where the function is at that particular point. But the result is it will be negative, which means my graph then is entirely negative on that interval. Because it's entirely negative on that interval, I have this portion of the graph is actually what is part of my graph, and I'll change it to blue because now that's part of it. So it's entirely negative on that interval. Okay, now between -3 and 2, I don't really need to use a sign chart because I have an or a y-intercept there that is positive. So everything on that interval has to be positive. So going from here down to this point, the graph has to be entirely positive. Now, the next thing that I'm going to explain to you will really speed things up. When we looked at multiplicity of zeros, what we discovered is if the graph was multiplicity 1, it would just pass through the axis. If the polynomial was multiplicity 2, then it would touch the axis and bounce away. If it was multiplicity 3, the graph would pass through, but it would take its time. So in the end, if a 0 had odd multiplicity, the graph would change signs. If you had even multiplicity, the graph would stay the same sign. So the same thing happens with these rational functions. So for instance, all of these asymptotes, the -3, the +3, oh, shoot. It's been at -2 the whole time here. Why didn't anybody stop me? All right, well, that's fine. I'll just change it here. So -2, +3 are my vertical asymptotes. +2 is my x-intercept. All right. Now, both of the asymptotes are multiplicity 1 because, you know, it's not like I had x plus 2 quantity squared in the denominator or anything like that. So those are multiplicity 1. Also, the 0 in the numerator is multiplicity 1. So at all of these, I change signs. So over the x-intercept, change signs. Over the vertical asymptote, change signs. So once you know one interval, then you can come up with the rest of them through multiplicity. So this will be negative, so it's actually just going down toward that asymptote. Then on the other portion, it is entirely positive. Let me scroll back up to the top of my graph. So it's going to look like this, right there. So that's a graph of my rational function. Let's compare that to what the calculator comes up with. And I'll drag this over a bit because I don't want to cover my graph. All right, so y equals, and I have x minus 2 divided by the quantity x squared minus x minus 6. Let's graph it. Just compare what it looks like. So it doesn't really look very much the same, although there are some similarities. Like for instance, if you see these vertical lines, which are kind of like vertical asymptotes, they are occurring at -2 and at +3. So it has that as a similarity. Next up, if you'll notice, on the interval that is from -∞ up to -2, this is all down here. Same as what I have on my graph. It's just on this calculator screen, it's going to 0 so quickly that the line is indistinguishable from 0 when you get to -10. Same thing kind of between these asymptotes. That part is there, it's just you can't really see it all that well. And this part right here is here, but you just can't see it all that well on screen. So you don't want to rely on the graph here in order to come up with the graph, because when you're doing a test, if you turn in something that looks like this, which is kind of like a cardiogram, one of those heartbeats, then you're not going to get credit for the problem because you obviously didn't do any of the analysis and you just copied what's on the calculator. However, if your graph looks like what I've shown here, you'll get full credit because you're clearly showing the asymptotes, you're clearly showing what's happened as the graph is going to positive and negative infinity. Like, you're showing all the different parts you're supposed to show. If you wanted to use the picture on your screen in lieu of a sign chart, you absolutely could do that. You could see where the graph is positive and where it's negative, then go with that. That's perfectly fine. But you don't want to just copy what's on screen because it's just wrong. All right, it's just not going to give you credit. Most instructors grade these problems based off of the analysis first, and then very few points are actually dedicated to the graph. So seeing the full analysis is usually what your grade is coming from. All right, let's do another one. F of x equals 4x minus 2 over x plus 1. So we need to find x-intercepts, y-intercepts, horizontal asymptotes, and vertical asymptotes. It's already in factored and expanded form since both the numerator and denominator are linear. We just need to identify each of these different points here. The x-intercept, if you're not sure the way it's written, you could always take that x-intercept, 4x minus 2, set it equal to 0 and solve. So 4x equals 2, or x equals 2 over 4, which is 1/2. So we have an x-intercept at 1/2, 0. The y-intercept, the constants are -2 and 1, so it's going to be at 0, -2. Horizontal asymptote, these two the numerator and denominator are equal degree, so the ratio of the leading term coefficients, 4 and 1, is going to be 4 over 1, or just 4. And the vertical asymptote is going to occur at -1, so we'll express this as x equals -1. Now we'll place all of this on the chart. So 1/2, 0 is my x-intercept. 0, -2 is the y-intercept. Horizontal asymptote at y equals 4. And a vertical asymptote at x equals -1. Now, I don't need a sign chart at all in order to come up with what's happening in this graph. Because as I mentioned, this graph, the graph is going to be bent toward these asymptotes. So in this interval, it's only going to be either one of these two. And the reason I know it's not the lower one is because there's no x-intercept down there. In order for me to go from positive to negative, I have to have an x-intercept. Since I don't have an x-intercept, this is absolutely not the graph. This is not the correct portion of my graph. All right, so let me change this one into blue to get the right coloring here. So this is what my graph looks like. It's bending toward those asymptotes, entirely positive in this case. Now, on the other side of the asymptote, the graph could be this one, but I think I could rule that out because if you'll notice, I do have x-intercepts and y-intercepts defined. So I have to pass through these points. So it needs to be this portion down here. So this part is not what I'm looking for. I will erase it. So there is my graph. So I didn't even need a sign chart. All right, next up, x squared minus 4 over x squared plus 3x plus 2. So let's express it in factored form. So this would be x plus 2 times x minus 2 the denominator, x, 2, and 1, and they would both be positive. Ooh, now look, positive 2 is a factor in both the numerator and denominator. That entire factor is going to disappear and leave me with just x minus 2 over x plus 1, where x does not equal negative 2. So negative 2 is a hole in the graph. So when I'm doing my analysis, I still have to get x-intercepts, y-intercepts, horizontal asymptotes, vertical asymptotes, but I also happen to have a hole in the graph here. And it's at negative 2, but I also need the y-coordinate of that hole. So if I put negative 2 into the function, that's reduced. So the x minus 2 over x plus 1. So if I put negative 2 in there, it would be negative 4 over negative 1, which is positive 4. All right, the rest of my bits here, the x-intercepts, I have an x-intercept at 2, so at the point 2, 0, a y-intercept at 0, negative 2, horizontal asymptote at y equals 1, and a vertical asymptote at y equals negative 1. So once you get used to all of these different things, it's relatively easy to come up with the analysis. Let's plot all this stuff that we have. X-intercept at 2, 0, y-intercept at 0, negative 2, horizontal asymptote at y equals 1, vertical asymptote at, whoops, I said y equals negative 1, but that's actually x equal. Let me change that. So at x equals negative 1, I make it a vertical line. There we go. And the hole in the graph was at negative 2, 4. So I'm going to plot that, but I'm going to plot it as an open circle. All right, now again, I do not need a sign chart, because when deciding if my graph is going to be on the left-hand side, if my graph is going to be above the x-axis or below the x-axis, it absolutely can't be this portion, because number one, I don't have any x-intercepts, and number two, I have to pass through that hole in the graph. Okay, so this has to be up here. So just kind of draw it to where I bend toward my asymptotes, but pass through that hole. On the other side, it's clearly going to be on the portion that is below the horizontal asymptote, because I do have that x-intercept over there. All right, another example here. To begin, we'll express this in factored form. So x plus 1 and x minus 1. So I have a common factor of x in the numerator that I've just factored out. All right, so x-intercepts, I have x equals 0, so 0, 0, and x equals negative 1, so 0, negative 1. So I have two x-intercepts there. I have a y-intercept. If I go to the expanded form, the constant in the numerator is kind of assumed to be 0. 0 divided by negative 1 is just 0. So the y-intercept is 0, 0. Next, horizontal asymptotes. The degree is higher in the numerator, which means I have it's top heavy. So there's no horizontal asymptotes, so none. The vertical asymptotes would be x equals 1. But there's one more thing that's special about this, and that is because the degree is higher in the numerator by 1, there actually is an oblique asymptote. So we need to figure out what that is. And unfortunately, the oblique asymptote is not quite as fast to determine as the rest of them, but it's not that bad. So we just have to use synthetic division. My original function, x squared plus x is over x minus 1. When I'm using the synthetic division, down here, this changes to a positive 1 in my synthetic division. The coefficients of my quadratic in the numerator are going to be 1 for the x squared, 1 for the x, and 0 for the constant. All right, and I go through this synthetic division, bring the 1 down. 1 times 1 is 1. 1 plus 1 is 2. 2 times 1 is 2. 0 plus 2 is 2. What's important is this portion right here results in x plus 2 when I change that back into a function. So that x plus 2 is the equation of my oblique asymptote. So y equals x plus 2. Okay, now putting this into a graph. X-intercepts, let's plot those. 0, 0, and 0, negative 1. Y-intercept is 0, 0, that's already on there. There's no horizontal asymptote, but I do have a vertical asymptote at 1. And I have this oblique asymptote at y equals x plus 2. So you're just going to graph a normal line. And that line is going to be have a y-intercept of 2 and a slope of 1. So my grid's kind of light here, but I'm trying to plot these points as closely as possible. But when I draw this line in, I'm going to draw it with a dashed line because it's an asymptote and not an actual line. So I'll just do a dashed line here. And that's my oblique asymptote. Now, when it comes to graphing, these asymptotes guide your function. So again, it comes down to either a graph could be on this interval, this piece, or this piece. Well, it has to be the lower one, because I have those 2 points that I'm passing through on that interval. So it has to be that lower one. So I can get rid of the upper one. And it has to be that lower one, which I'll just leave in green because I don't want to erase it. All right, now the other side, my graph has to bend toward these asymptotes. So it's either going to be that, or it's going to be this. And I assure you it can't be this because I don't have another x-intercept for my graph to pass through. So it absolutely can't be this side. So I'm ruling that out completely. And there's my graph. And again, you could use a sign chart. And a sign chart would tell you basically the same thing. That on that interval you have to be entirely positive, and the only part from 1 to infinity that's entirely positive is the one that I've drawn in green. So that's that. Let's do one last example where we are going to identify a rational function with the following graph. Now, this may seem like it's going to be relatively difficult, but based off of the properties that we know, it really isn't going to be that difficult. So, for instance, there's different things that we know about these. We know locations of x-intercepts, y-intercepts, vertical asymptotes, and horizontal asymptotes. X-intercepts, I have one here at 0 and at 2. So the point 0, 0 and the point 0, 2. Those are x-intercepts. Y-intercepts, 0, 0 is a y-intercept. There's only ever going to be one y-intercept. Vertical asymptotes, looks like I have one here at -3 and at, oh, I'm sorry, that's not -3, that is -1. -1 and +3. So x equals -1, x equals +3. The horizontal asymptote I have at, looks like that is at 1 based off the scale here. Looks like on this axis the scale is by a half. So just be careful. This is y equals 1. Okay, so using those, I think I could come up with a pretty decent guess as to what this function is. For instance, in order to get x-intercepts at both 0 and at 2, I would need a factor that has a 0 at 0, which would just be x, and a factor that has a 0 at 2, which would be x minus 2. Because if I plug in x equals 0, that numerator becomes 0. And if I plug in x equals 2, the numerator becomes 0. The denominator would have to have factors of x plus 1 and x minus 3, so that I would have asymptotes, vertical asymptotes that is, at -1 and +3. Now my horizontal asymptote is pretty well taken care of. The horizontal asymptote is, if you look at the degrees, the degree of the numerator is 2, because I have 2 zeros there, and the degree of the denominator is 2. So the degrees are equal. But tell you what, let me multiply it out. So this would be x squared minus 2x all over x squared minus x minus 3x. So minus 2x minus 3. And the degrees are equal. So that means I have a horizontal asymptote at the ratio of the leading term coefficients. And since that horizontal asymptote is at 1, my leading term coefficient ratios, so I have a 1 here and a 1 there, that works out. So I don't need to do anything further for those. So I have a function now that meets all of these criteria. It has zeros in the numerator for these locations. The ratio of constant terms would be 0 over -3, so the y-intercept matches up. The vertical asymptotes match up, and we just showed the horizontal asymptotes match up. So that works out just fine. There's a function for that particular graph.